Yeah, if you want.
So
but I didn't do anything today.
That's also you don't mind not.
I just didn't know what to do, and I didn't think about it until too late to organize anything.
okay, I don't know what to do either.
I mean, we generally have a student lunch review, but it makes a lot of sense because it happens right afterwards.
Yeah.
Yeah, student lunch review, but what about Thursdays, like track?
Yes, it's meant to be, well, whoever faculty and wants to, connect to the speaker. $100.
$100. So you went around the
$200 for
I should have paid for my burrito.
You still could. You have the receipt.
Well, what's the speaker with you?
He was.
Okay.
Then
yes.
He also ate a burrito.
Oh, you guys should pay for 2 burritos then.
Yeah. He paid for his own burrito.
Well, yeah, you have the,
He was helped by the government.
did you go somewhere to get burritos or did you go to you?
Zero. The place up in the biophysics building or bioengineering building. Past
The one that used to be pizza.
the one that used to be, yeah, sort of pizza. And
Pizza plus
sandwiches. It used to be awesome.
It used to be very nice.
And it's still quite good, but it's not it's really nice compared to. They have good beacons.
They have really good things for being on campus.
Yeah.
So I'm posting next week's schedule,
Yeah.
which is why I'm asking this.
Right.
Sorry. It's only in the daytime.
And that's a cushion piece.
He's getting network on Sunday. So I probably will do something for small, but
No alcohol. Yeah, no alcohol. No alcohol at dinner.
I didn't know that restriction. I think I may have violated that before.
I have violated.
Well, do you mean it can't be paid for?
It can't be
Can't be
paid
paid
for.
Sure. You can still do it.
Sometimes it is paid for.
Right. We can never pay for alcohol
The
ever.
most,
that's very true of a lot of places.
at UW, the most memorable lunch I had with the speaker, we had grad student lunch with the speakers, was the speaker who bought 3 pitchers of beer for the grad students at lunch.
How many grad students were there? That's a relevant part of the story that should not be left out in the retelling.
It works better on the back board.
Yeah, sure. But not. We didn't even plan that.
Probably have, you good?
I'm great.
Facilities.
Like all of the facilities here are like around corners and like I think the people that built these buildings like didn't ever use the bathroom, or like they did it before they came to work, or I don't know.
I can't think of any labels. We had a astronomy colloquium this year.
It's maybe our first one, yeah. We have a couple coming up now.
One next week for cosmology.
Oh, and Dave Strader was going to be, but so
What did Dave Spurgeon cancel on Neo? He's too busy taking over the world.
hiring 100 astronomers.
For 3-year positions, so?
No, they're going to hire like 20 permanent positions.
But they're not 100% positions, right? Their model is like they pay part and like somebody else pays part.
Really? Yeah. So who's paying the other part?
What a great question. Columbia and that's how they're doing things. So, yeah.
I'm sure NYU will be a participant in it. I can't imagine they're going to save 20 people half time.
Well, yes, right. Like Hogg is now being paid part time from this.
It's not a half-time tomorrow, is he?
I'm not sure. My understanding is that most of the new hires are being done under a partial funding thing from Flatiron. I'm not saying it's all of them. There might be some that are full.
What is Curtin?
Curtin is a university in Perth, Australia, at nearly the other end of the earth.
I had a phone con with someone from there last week. They're 9 hours behind the 24 hours ahead, so they're... I do math, 14 hours ahead.
For Japan, I always think like you do. behind, but then you just add day.
As an example of how everything is local politically, the people at the University of Western Australia, another university I've never heard of and don't care about, think they're way better than the people at Curtin, who are like a block away from them or something. It's very silly.
Also, like,
We're way better than people at BYU.
I was actually referencing that. That was the subtext to the. We're the only state university in Michigan. Maybe you've heard that.
He's not Laura. What about the University of Michigan?
I don't know what university you're talking about.
there are no consequences.
At least not in physics or astronomy.
They don't have any astronomers at all. It's nice that there are lots of astronomers in Michigan. Wayne State now has a bunch of astronomers, or at least a few.
So Michigan State are you a department of physics and?
We are physics and astronomy, so we are a 10 faculty member group inside the physics department, right? Which is 65 people or something, right? It's enormous. So.
You have 65 faculty in physics?
Yeah, it's an enormous department. So.
Do you know how many students from the university?
I mean, undergrad only about 40,000, including grad students 50,000.
Okay.
All right.
So we're a top 10 university.
Jay's already busy introducing himself.
I'm answering questions from the audience.
It's already interactive. We have Dr. Jay Strader with us from Michigan State. Jay did his PhD at UC Santa Cruz and then was a postdoc at the Center for Astrophysics, where he was both a Hubble Fellow and a Menzel Fellow in succession. And
That's where I met you.
And that's where we overlapped for several years, and including sharing an office at one point. And he's now at Michigan State for the last 5 years, and he's recently won a Packard Foundation Fellowship, and also is funded and everything. And he's going to tell us about, he's kind of switched fields in recent years, and he's going to talk to us about black holes and globular clusters. Either way. That's my one job.
Thank you, Adele. Yeah, so my talk is called Black Holes and Globular Clusters. This is a large research project that involves a whole bunch of people to big international collaboration, including a bunch of students and postdocs and other faculty members at Michigan State, where I am, but also people here. Curtin, we already have talked about, so that's in Perth, Australia, right? So that's about as far from the US as you can get. We also have Canadians at the University of Alberta, and then Nil is also a collaborator here. We have a German collaborator who didn't make the cut. She fell off the edge of this list there. So it's a big collaboration. So this is called Black Holes and Globular Clusters, but really it could be called How Do You Make a 29 plus 36 solar mass binary black hole? So right, the context of what I'm going to be talking about is this result we've all seen, right? The detection of the first gravitational wave signal by LIGO, which was announced almost exactly a year ago, right? So we're just coming up, it's just been a year since this was first announced. So this beautiful signal that was seen in both the Washington and Louisiana detectors, and it was a binary black hole, right? This is a very exciting thing that happened about a year ago. So in the context of astronomy, right? So I'm an astronomer, why is this exciting? We go to the New York Times, right? And what the New York Times would tell you is that LIGO told us that we confirmed Einstein's theory by detecting gravitational waves, right? So the main reason we should be excited is that Einstein was right. But right, we kind of already knew Einstein was right, and we've had pretty strong evidence. We even had a Nobel Prize showing that the basic theory about the emission of gravitational waves by close, compact binaries, in this case, the in-spiral of two neutron stars, one of which is a radio pulsar, and thus can be timed with exquisite precision, where we already had an enormously good match between the basic predictions of general relativity and some observations, in this case, of radio pulsars. This is not the only one, right? There's a bunch of these things, including one where both of the sources are pulsars, and that allows even yet more exquisite constraints on deviations from the basic theory of general relativity. So it's not that there's nothing to learn here, right? Obviously, general relativity is an important theory. We should test it to the ends of what we can possibly do. But from the basis of astronomy, we kind of already thought that gravitational waves were probably correct, and if things were merging, we probably would see them. So from my point of view, the most remarkable properties of the first LIGO detection was that it was black holes merging rather than neutron stars, right? We knew at some level neutron stars had to be merging because we knew about binary neutron stars that were very close together. Their evolution matched the predictions in general relativity, so we knew at some rate those neutron stars had to be merging. So that was a certain source class for LIGO if it ran long enough and was sensitive enough. People thought there might be binary black holes, we weren't sure. And the really remarkable thing is that the black holes were so massive, right? 29 and 36 solar masses. So if you look at the inferences for what the properties of these two black holes were from the original Abbott paper, right? We have 36 and 29, actually with pretty big error bars. In fact, they might be about the same mass, consistent with the uncertainties. The final black hole mass was 62, right, which is less than the sum of these, because, right, that extra got radiated away during the black hole merger. And, right, these basically, under GR, serve as standard candles, so you can actually figure out how far away that source merged. So we have 29 plus a 36 solar mass black holes. These black holes are nothing like black holes that we know about in the local universe. These are much heavier than the black holes that we know about. And there are good reasons, before this ever happened, to be skeptical about the idea that LIGO would have found binary black holes that were massive like this. And that's because getting two black holes in a close enough binary, such that they would merge in a Hubble time, is really hard. The main reason is that we think black holes come from massive stars, and what happens with massive stars is as they evolve towards the ends of their lives, which happens very fast, they get big and they eat each other. Right? If you just run a model for what two massive stars are going to do that are going to turn to black holes that close to each other, will eat each other. And then, on the way to turning into a black hole, typically, you have a supernova explosion, and even if this didn't happen beforehand, this happens, right? So the supernova goes off and that destroys the binary. You know, they still survive, but they're not bound to each other anymore, such that they can merge to emit gravitational waves. So you said, okay, I'm going to try to get around these problems, and I'm going to model how this can happen, how I can get binary black holes. You go and you look at papers that look like this, which looks like gobbledygook to you, and that's because that's what it is. It's an enormously complicated set of a bunch of individual steps that are poorly understood. So you have to have two massive stars that are pretty close to each other. They have to evolve. They have to have what's called common envelope evolution, where one of them swells, and it causes the other one to spiral in close to it, but not so close that the stars actually merge. And you got to make two black holes, so you got to do this whole thing twice. You got to not. It's very, very complicated. And it has a bunch of steps that, unlike, say, evolution of stars like our sun, which we understand pretty well, we really don't understand the way in which massive stars evolve very much at all, especially when they get in close binaries like this. So it's certainly the case that something you can say for sure is that even if this might happen occasionally, what the predicted rates of these black hole mergers was extremely uncertain. So we don't know really how often it happens, and before the LIGO event happened, there were a bunch of people that said this will happen never. There are some people that were hopeful that it would happen sometimes, but the a priori prediction of how many of these things is occurring was not very high. There is another way, though. And the origin of that other way is globular star clusters. So globular clusters are these collections of 10,000 or 100,000 or a million or more stars. And these clusters are found in substantial numbers among all big galaxies, including our own Milky Way. What happens in a globular cluster is because they're so dense, if you can start with little black holes in these globular clusters, they will make their way to the center of the globular cluster through gravitational interactions with other stars. And once they're there, they can make brand new binaries. So if you're outside of a cluster, if you're in the regular Milky Way field, right, that's like what the sun is, we're just sitting somewhere, the only way you can be a black hole binary is if you were born that way. But if you're in a globular star cluster, you don't have to be born that way. You can make a new black hole binary. You can do it dynamically. And one thing is the physics of how this works inside of a globular cluster, it's actually pretty simple. It's basically just gravity. If you retain black holes inside of a globular cluster, they will come together in the center, they will make new binaries, and then some of those new binaries will probably, one day be LIGO sources. So what do we know about rate predictions specifically? So if you don't take, this post hoc stuff after the LIGO event, and you look at what the LIGO collaboration was predicting as a range of expectations before any LIGO sources were ever detected, what they are saying for the black hole channel, if we recast it in some sort of reasonable terms in terms of our current horizon, is that the number of expected black hole mergers is from something like nowhere, right, so something like 0.1 on the little end, up to a few hundred per gigaparsec per year, right, where a gigaparsec is something like a reasonable guess as to the current LIGO horizon value for black hole mergers. There's this enormous range here, where this was the super optimistic ones, and this was basically we think this will never happen. Well, if you look at what we know about black hole mergers from the recent LIGO events, the range from the two events that are for sure, and this one sub-threshold event, which, if they hadn't have found the detections, this probably would have been called something like, evidence for a gravitational wave merger in the local universe. Right, if you look at this compared to what the noise level was, this is still a pretty convincing event. The range now is something like 10 to 240. So this low mass end, this RAN where we thought this never happened, that's been totally eliminated. So one possibility is that there is some way of doing this in the field that we just don't understand because it's complicated. And the other possibility is that this dynamical formation is important. So as you might guess, I'm going to be talking about this dynamical channel during this talk and about the evidence that maybe this is actually happening. So like I said, this is a globular star cluster. This is the cluster M3, which is one of the clusters in our Milky Way galaxy. These are massive. These are old, right? So the oldest ones are as old as the age of the universe. So within the uncertainties we can guess them, although some are slightly younger. In the Milky Way, we have about 160. If you look at a nearby big elliptical galaxy, they might have tens of thousands of these globular clusters, each of which of these things is a little factory for dynamically, actively forming new binary stars in the center. So how do we quantify this? Not just thinking specifically about black holes, but other compact binaries that you might make inside of a globular cluster. Well, one thing we know is that by doing studies of compact binaries, not just containing black holes, but also containing neutron stars, both inside of globular clusters and in the outside field populations of galaxies, which is that globular clusters produce compact binaries a factor of 100 more efficiently than the field populations do. So globular clusters really are factories for making compact binaries. If you look at a bunch of big elliptical galaxies, half of the X-ray binaries in the entire galaxy are found within globular clusters, even though globular clusters make up 0.25% of the total number of stars in those galaxies. So globular clusters are these enormously efficient factories for making X-ray binaries. Now I've told you that one way to see that visually is to compare an optical image of a globular cluster, in this case the globular cluster 47 Taka, with an X-ray image where the X-ray light is probing these compact binaries and the X-ray emission is coming from an area very close to the compact object. And you can see in the core of this globular cluster, it is just lit up with these things that look blue and reddish and orangish there, and those are all individual X-ray binaries in this globular cluster 47 Taka. So what do you know about the physics and the phenomenology of these low-mass X-ray binaries here, where we say low mass because the secondary, the object in the binary that's not a compact object, is not a high-mass star. It's not a star that is living a very long time, but it's a relatively low-mass star, and that's what you expect, because in one of these globular clusters that's old, all of the high-mass stars have died out, and what you're left with are relatively low-mass stars of the present day, about the mass of the sun or less massive. So if you wind up with a binary with a compact object of some sort, so either a neutron star or a black hole, I'm not talking about white dwarfs here, but those do share some of the properties with these objects, and one of these secondary stars here is if they get close enough, the secondary star will overflow its Roche lobe, and the matter will flow through the inner Lagrangian point. It'll conserve angular momentum and form an accretion disk around the compact object, and that accretion disk will glow across the electromagnetic spectrum. So you can get bright optical, especially UV emission from the accretion disk. You can get X-ray emission from the inner parts, either from the inner part of the accretion disk or from a corona that's actually formed through an unknown way around the compact object. We also get these jets that come out of the accretion disk, actually both for black holes and for neutron stars, so they're brighter for black holes. And those produce radio emission, the specific jets. So you can see there's a lot of different ways that we could try to select out these objects that are showing up as low-mass X-ray binaries. field of the galaxy, right, we can find these X-ray binaries as bright X-ray sources. We can study them. In the Milky Way, it's less than half are in globular clusters, only maybe a quarter in globular clusters, so most are in the field. And about a third of them, when you go and you do detailed studies of the dynamics, measure the mass of the compact object, you infer that it's a black hole. So we actually know about a bunch of these X-ray binaries in globular clusters, as I told you. So you might say, oh, well, if about a third of the ones that we see in the field are in black holes, if you go to globular clusters, maybe we expect the same thing. In fact, we know that all of the bright X-ray sources that have been discovered in Milky Way globular clusters do not contain black holes. They are all neutron stars. And we can tell they're neutron stars and not black holes, even in the cases where you've not been able to map the motion of the star around the compact object to measure its mass. It was a kind of what are called type 1 X-ray bursts. And that's because a neutron star, it accumulates mass that it accretes from the companion. And once in a while, when it gets enough mass, that mass undergoes a thermonuclear runaway, you get a bright flash of X-rays, and then it fades back down. Black holes, right, in our standard understanding, don't have surfaces, no mass accumulates, it just advects past the event horizon, and that's the end of it. So if you see an X-ray burst in your object, then you know that it's a neutron star. So, where are the black holes in globular clusters? The fact that we had not seen any led to this sort of theoretical explanation for why the black holes in Milky Way globular clusters were missing, maybe 10 or 15 years ago. So, we know that there ought to be black holes in the star, and the reason there ought to be black holes in the star is that we think massive stars make black holes. If you look at star clusters, they make massive stars just like any other area. And so the most massive of those are going to leave behind black holes, and depending upon the initial mass of the globular cluster, you maybe start with 100 or a few hundred or 1,000 black holes to start with. And those are made over the first, 10 million years or so of the lifetime of the cluster. So compared to the 10 billion year age of the universe, right, basically nothing, right, it happens like that. Maybe you lose a few of these to natal kicks, right, so depending on your exact formation mechanism for the black holes, maybe they get a little kick, and they don't stay in the star cluster. But if you look at what black holes look like in the field, probably they can't all get kicks to eject them from globular clusters. You need to keep some at least around for a little while. What happens next? These will relax to the center of the globular cluster, and what that means is that when they have gravitational interactions with other stars, both close interactions, but actually also the sum total of the more distant interactions with stars, these will tend to equalize the energy among the stars, and since these are heavier, that will cause the more massive objects to condense down into the center. And since they're a factor of 10, on average more massive than the typical star of one of these clusters, this, what's called mass segregation, actually happens relatively quickly through these encounters. And so all these black holes, which, at the start they could have formed anywhere in the cluster, all wind up at the center of the cluster. What happens when they wind up in the center of the cluster? Well, it's that thing that I suggested to you earlier. What's going to happen is those black holes will have 2 and 3 body encounters with other black holes and other heavy things like neutron stars in the center. And what happens is a lot of them are going to get ejected, right? So they have these very close things, and you'll have a very close encounter, and boom, you lose the black hole. Now, the black hole doesn't disappear from the universe, right? It's lost from the star cluster, right? And in fact, it's possible, right, that you can make black hole binaries in these close encounters in the centers of star clusters that get ejected out into the field. And some of them, right, the ones that have the right, eccentricity and semi-amplitude, they'll wind up merging the Hubble time. And so you might have a black hole binary that was formed in a globular cluster. It got ejected a long time ago, but it was still originally in the globular cluster. It was still made dynamically rather than in the field. That is actually a possible origin for, at least some of these LIGO things. You've got to fine-tune, because they really, this is all happening very early in the lifetime of the globular cluster, and we're seeing them merge with LIGO right at the present day. So they have to have the right distance to do that, but that, that's quite plausible. That might be happening for some of them. So you've got this ejection thing going on, but as you might guess, right, this ejection is not going to continue forever. So the efficiency with which you can eject black holes depends upon what the density of black holes is in the core of the globular cluster. And after you've kicked out a whole bunch of them, the density of the black holes in the center of the cluster isn't that high anymore. They don't encounter each other very often. And so the efficiency of the black hole ejection is going to go down. There were sort of analytical arguments that basically assumed that the black holes went to the center, they became decoupled from the other stars, and they fully ejected each other, maybe leaving behind, one or something. But if you do, full computer simulations of this, you see that basically never happens, or it happens only very rarely. Right? Once the number of black holes drops to, something sort of modest, tens of black holes in the center, they are no longer ejected efficiently. They are not totally decoupled from the other stars. And so, right, I put here question marks indicating, right, the fact that this whole story might not fully hold. So the first observational turnaround in this story, the first idea that something other than what we previously thought might be happening, was this compelling evidence for an accreting stellar mass black hole, not in a Milky Way globular cluster, but instead in a globular cluster in a big elliptical galaxy in the Virgo cluster. So this was first found as a variable X-ray source that was extremely bright, so much larger than Eddington luminosity for a neutron star. And it was found that this X-ray source was highly variable on relatively short timescales. And that was relevant because it meant that this, super Eddington luminosity for a neutron star isn't just due to the superposition of a few X-ray binaries in one cluster, which we know happens sometimes, but that this emission is due to a single source. So that was the first suggestive thing. Then when people took optical spectra of this source, they found something that's never been seen in any other globular cluster, which is that rather than sort of a boring spectrum absorption lines that, right, sort of just looks like the spectrum of our sun, or a star a little bit cooler, they saw this extraordinarily broad emission in the oxygen 3 forbidden line. And what this means is there's an enormous amount of energy being channeled into this one line that's a forbidden line, so it means it must be coming from a region that's not particularly dense. And so if you put these two observations together, really the only model that makes sense is that you have a stellar mass black hole in the core of this globular cluster. It's actually accreting from a white dwarf, and the way you know that is that there's no hydrogen emission or helium emission here. And so it's coming from something that's only giving you an oxygen line in the optical, and the most natural thing is a CO white dwarf. And an enormous amount of the luminosity of the accretion from this white dwarf is being channeled into this O3 line, with some of it staying on the X-rays. So it actually turns out the nebula associated with this thing is not a point source. If you look at what the Hubble Space Telescope is resolved spatially, and it's several parsecs in size. So surrounding this system is a several parsecs in size nebula being driven by an outflow from a stellar mass black hole accreting from a white dwarf companion. Now, there's nothing like this in the Milky Way system, right? Anything that was this way would be extraordinarily obvious. We would have known about it. Would have been famous for decades or centuries. But right, what controls the accretion rate onto one of these objects? Right, is driven essentially by the stellar evolution of the secondary and eventually by gravitational waves when they become close enough to each other. And for every one that's like this, accreting at this very high rate, right, they can't do that for very long. And so there must be a much larger population that's accreting at a lower rate. Right, so here I'm just saying this thing here is the sort of tip of the iceberg. And what we want to go after are these things down here, these fainter things, these things that are harder to find. So that's the goal of our observational work. All right, other than explaining the LIGO sources, why do we care about this? Well, right, the LIGO thing's in front of it. So I've made the case to you that we should think about the possibility that the dynamical formation of black hole binaries might be important. It actually might be important also for black hole neutron star binaries and for neutron star binaries. We know for sure neutron star binaries do form in the field, but a lot of the clusters are also full of neutron stars, and so they can make an important contribution to that. Another thing is that black hole formation at lower metallicities, at lower levels of chemical composition, could also be important. So if you look at models of how massive stars evolved, what you typically find is that the expectation is that the remnant left behind will be more massive as you go to lower metallicities. If you look at things that are forming in the field population, those are high solar metallicities, maybe supersolar, and those are not expected to produce 30 solar mass black holes like was found in the first LIGO then. However, those things emerge naturally at low metallicities like you're finding in globular clusters. So that's another reason to think that globular clusters might be relevant for forming LIGO sources. Another thing is, as I told you, right, these LIGO sources have black hole masses that are substantially larger than any of the black hole masses that we see for X-ray binaries in the Milky Way. And all the X-ray binaries we see in the Milky Way all have some of these same biases that I told you was a problem for forming LIGO sources in the first place. They have to have this very close, complicated binary evolution. In a globular cluster, that's not the case, right? You can form the black hole however you want, has a single star and a binary that's relatively close, and then you can give it a partner later on. And so the way in which it evolves as a binary is decoupled from the initial formation of the compact object. So, the black hole masses you might find from these systems are, at least different than the biases in the black hole masses that you find in the field. Alright, so instead of why we'd want to do this, instead of why this might be interesting, I kind of told you that it might be hard. So why is it hard, and what exactly are we doing observationally to make progress on this? So I told you the low-mass X-ray binaries, right, that is neutron stars or black holes that are accreting from low-mass companions that are close to them, emit across the electromagnetic spectrum. And the way in which we are attempting to isolate ones that might contain black holes is by simultaneously looking at the X-ray emission and the radio emission from the source. The X-ray emission we think is coming from a region very close to the compact object, and the radio emission we think is coming from these jets, these bipolar jets that are being ejected above and below the compact object, above and below the plane of the binary star. And what we're exploiting is an observational correlation between the radio emission and the X-ray emission for black holes and for neutron stars. So as we're showing this plot, so here we have the X-ray luminosity between 1 and 10 keV, and if you want to know Eddington luminosity for a neutron star, that's about here. And Eddington luminosity for a 10 solar mass black hole would be up here somewhere. So this correlation is only valid for objects that are accreting at a few percent or below or Eddington, right? So we're not looking at the very brightest things. They accrete in a totally, actually very physically interesting, but a totally sort of different regime that we're looking at. The black points here are black holes. These points here, these stars and cyan points are the neutron stars. And you can see the black holes sort of do funky things. There's a bunch that seem like they lay on a nice linear correlation, and there's a bunch that sort of do inefficient accretion there. They sort of dive down and then rejoin. That's actually not a totally different set of objects. Sometimes the same black hole will sometimes evolve as it's outbursting along the top one, and sometimes it will go in that sort of peg leg of evolution. That's not actually totally understood. But on average, there's an observation that the black holes have brighter radio emission than do the neutron stars at a fixed X-ray luminosity. So the basic idea was that we'd get a bunch of X-ray luminosities for sources in globular clusters, then we'd measure a bunch of radio luminosities, and we'd look for ones that were particularly radio bright, things that had a high ratio of radio X-ray luminosity. We'd select those as the most likely candidates to be black holes, and then we'd follow them up on other wavelengths to see if we could really confirm that or not. So that's what we've been doing. Now again, these are all relatively bright things, easy to study. The objects we're looking at are really more in this regime down here, where things are very, very faint. As you might guess, they're more faint things than bright things. The reason they're on this plot is that we just don't know that many about them, right? So they're faint, so it's hard. Yeah?
What's the difference between the two light blue lines?
So, the difference between the two light blue lines is that nobody has the faintest idea of what neutron stars do down here. And so no neutron stars have actually been observed to fall through quiescence. And so these are two different attempts to fit a line to this sort of hodgepodge of neutron star observations here. So things are so poorly known for neutron stars, nobody even knows. Right, you're getting to be several orders of magnitude different in the predicted radio luminosity for neutron stars once you get down to these levels. Right, the neutron stars, when they outburst, they go through the outburst very quickly. And so you only have a couple of days to catch it from somewhere here where it's very easy to study and somewhere here where it's totally impossible to study. And you've got to coordinate your observations between your space telescopes that are doing the X-rays and your ground-based telescopes that are doing the radio. There are several groups trying to do this better. It's hard. Alright, so obviously, right, this is a really scientifically interesting problem. We are not the first person to think this problem is interesting. Why can we do this now when other people haven't been able to before? And the most important advance is this technological advance of the upgraded Carl G. Jansky VLA, the Very Large Array. So this is the radio telescope in New Mexico, right, the one that was in the moon contact. This is this radio telescope that was initially built in the 1970s, right? It actually came in under budget, right? That's not something you hear a whole lot about happening these days. And it was this beautiful, totally forefront observatory, but right, it aged. It had old electronics and things. And what happened was, these dishes are more or less exactly the same as the old VLA that people have used for 30 years, but but they entirely replaced electronics in both the receivers and the back ends of the telescope. Then the result is that if what you're doing are radio continuum observations, and that's what we're looking at for these radio jets from objects, this is an enormous upgrade of a factor of 20 in the amount of the bandwidth you have access to instantaneously for the VLAs. Even though the dishes are exactly the same, it's like you have this whole new powerful radio telescope. So we decided to use this upgraded facility to do this search for radio emitting objects in globular clusters. So because we weren't sure about the sorts of objects in which we'd be most likely to find these candidate black holes, and because we didn't want to bias ourselves ahead of time for the sort of things we might find, we took a very wide variety of objects. Our total sample of Milky Way clusters is about 50 clusters, right? So that's almost a third of the entire cluster population of the Milky Way. But I've just put a sample of the clusters we looked at here, so you can get a sense that these clusters have a wide variety of properties. Some of them are extremely compact, like these clusters. Some of them are much looser, right? Some of them are very massive. Some of them are lower massive. And so the idea is that if we can, find some candidate black holes in some of these objects, then we can correlate it with the cluster properties. We can test our models about how we actually think these, black hole binaries might be forming inside the globular clusters. All right. So how does it actually look when we do this? So I'm going to show you a comparison of a radio image from the very large array on the left panel, and here on the right panel is an X-ray image, in this case from the Chandra X-ray Observatory, which is the X-ray observatory that has the highest angular resolution. What you're seeing here is the center of the cluster marked with a little red cross, and you see a bunch of these little white things, and those are all the X-ray sources in the cluster. You can actually see this cluster here, which is the cluster M62, which is chock full of X-ray sources, and all of these are X-ray binaries of one form or another. But you can see only one of these X-ray binaries, the one that's circled, shows up as a clear radio source. The other ones are not detected in the radio.
What is the significance of that?
So this one has a significance of 9 sigma. Yeah, approximately that. And this is one of our favorite candidates. You can see, right? You can imagine if you had a radio telescope that was a factor of 20 worse, this isn't there, right? That's why we are having some success in doing this when nobody else had previously, which is that these suckers are faked. So you can see, right? You've got all these X-ray sources. Only one of them is clearly detected in the radio. And so this one looks different than the other sources. So these are the sorts of things we're going to be going after. So just so I can prove to you, right, that I'm not circling scruff in every image, right? Like, we have plenty of clusters that look like this. So this big circle here is the core radius of the cluster. That's the radius which you'd expect to find most of the compact binaries because they're mass segregated. There's nothing there in the center of the cluster. I just want to point out, right, so this radio image, right, you're focusing it on the glob of the cluster, but right, it's picking up radio emission all along the line of sight. And so you things like this here. So this is almost certainly an AGN in the background. A few of these are star-forming galaxies in the background. These images are actually, the images we're making for this are some of the deepest radio continuum images ever made in history. So we're getting down to typical noise levels of a microjansky RMS. And we have that for, 50 clusters. So we have very sensitive images. So we see galaxies, everywhere in these images. Right, that's why we have to focus our attention right at the center of the globular cluster, because that minimizes the contamination. In theory, we could have, X-ray binaries here at larger radii in the cluster, right? They're harder to find. All right, so let's talk about this first candidate that I mentioned, the one in the globular cluster M62. So M62 is a relatively massive Milky Way globular cluster that has a relatively large core. So this is one of the reasons we went after it. So again, this is our radio image, this is our X-ray image. We're looking at this source here. You can actually see in red, I've circled another image of the radio source, and this is actually a radio pulsar. So this is a previously known pulsar that had been discovered in the globular cluster, and it is showing up in our radio continuum image, but it's barely / not detected in the X-rays. So pulsars are something which are quite bright in the radio and not typically very bright in the X-rays. We can distinguish pulsars from black hole candidates in our data on the basis of the fact that the pulsars have very steep radio spectra, so they're brighter at low frequencies, whereas the black hole candidates, the emission from the jets is approximately flat, and so you look at that, the same brightness across the frequencies that we're looking at. a slightly recast version of the plot I showed you before, but the data is very similar. And you can see where this candidate in the cluster M62 falls, which is exactly on this correlation for the stellar mass black holes that I showed you before. And in fact, it's very close to this object called V44 Sig, which is a field stellar mass black hole that is a period of about 6 days. It's one of the best studied stellar mass black holes that we know about, actually. And so at least in X-ray versus radioluminosity, it sits very similar to this point in particular. But this, by itself, just this radiant X-ray data, right, that's not, just, it doesn't convince anyone of anything. We haven't learned anything, really, so far.
Sorry.
Yeah.
Can you remind me how this was made in the first place, where you could discriminate the black hole sources from the radio sources? Was it from local dynamics, or how is this curve? How are they discriminated in the first place?
Yeah, so all the black points on this curve are dynamically confirmed black holes.
Okay.
So in every one of these cases, this is something where you've done a mass estimate, and the mass estimate is above the highest that could possibly be for a neutron star.
Okay, and that was in extragalactic sources? That was
So these are all Milky Way sources. Yeah, these are all Milky Way sources, right? So, how basically, until we're starting this thing where we're finding these new candidates, how every stellar mass black hole in the Milky Way has been found is there's an X-ray outburst, right? They're called X-ray novae. It gets really bright in the X-rays, right up to, typically the Eddington luminosity, maybe slightly less than that, and they slowly fade. After it fades away, you look and see if you can find the secondary star that orbits the black hole, and then you study that star, and that tells you whether it's a black hole or not.
Okay.
And many of these are the same data point, the same black holes.
That's right, so the black holes move up and down this correlation, right? So they go into outbursts, they get bright, and they fade down and get faint again.
Okay, that's what I was really surprised about, that there were so many confirmed.
That's right, so there are about 25 dynamically confirmed black holes, stellar mass black holes in the Milky Way.
And there must be 100 or so data points on there.
That's right, and I'm not even sure all 25 are on here because there's not good simultaneous radiant X-ray data for all of them.
Okay.
Yeah. Right, right, this happens maybe once every couple of years, and that's the only way in which we have found new stellar mass black holes in the Milky Way.
When was the first one found in this way, roughly?
So, 1970s?
Oh, a long time ago. Okay.
Right, there are a few black holes. They typically have more massive companions that are persistent X-ray sources. They just accrete at a substantial fraction of Eddington all the time. But most of them are these soft X-ray transients that have been discovered, since we started putting things up in the X-ray satellites up in the 1970s.
Okay.
Yep. So the neutron stars also do outbursts, and the way you tell it's a neutron star is you look for type 1 X-ray bursts, or you hope you get lucky when it fades enough such that you can study it secondary to see. There are many more black hole candidates, so these are things that outbursted, and there's nothing, the secondary is too faint, and so we can't get a dynamical measurement of it, and so we just don't know.
Is it possible that some of those, the secondary would be another black hole? Or you need to have a stellar source to have the outburst?
Right, so these outbursts are typically thought to be from this limit cycle accretion phenomenon, where you get enough mass built up to the accretion disk, the opacity changes, right, once the disk temperature gets up to 10 to the 4, and you just dump all this material
But the
onto the
accretion
compact
disk is
object.
formed through the secondary.
The accretion disk is formed through the secondary, or if it's a massive companion through wind. So you can also get wind accretion.
Okay.
Yeah.
Yes, in the previous plot, you showed that it's a similar plot like that one. Showed that it's possible to have like white dwarf here.
Yeah.
To go above this line, so there are possible confirmations from white dwarfs.
That's right. So white dwarfs. So this is a white dwarf flare that happens there. So white dwarfs occasionally, a few of the nearby white dwarfs we know, show very short flares that last maybe 5 or 10 minutes that get up as bright as these, and they fade back down. So all of the radio sources I'll be showing you these are all persistent radio sources. So we don't think they can be explained by white dwarfs, but nobody knows anything about accretion, so who knows, right? Maybe we're looking at a different population of white dwarfs, maybe they have different magnetic fields. The ones that show bright radio emission, these are all intermediate polars. So these are ones where both there's an accretion disk and some of the emissions channeled onto the white dwarf. Whether that radio emission would in detail be persistent or look like our sources, we don't think so, but we don't know.
The black holes that are below 10 to the 28th ergs per second,
Yes.
were those just happened to be very close by, so they were seen before this upgrade of the BLA, or?
So some of these points, so like this simultaneously measurement, this happened since the VLA went online, right? So we knew there was a black hole there, but we didn't have its radioluminosity because it was too faint to be seen by the previous generation of things. So these two measurements, I think this one was barely done with the old VLA. Yeah. And this one is bright enough that it was done. These do tend to be relatively close to the Milky Way, but not all of them. Some of them are to the sun. I mean, some of them are a little bit further.
But so the upgrade really extends. They
That's right. So
reach downward on this block.
That's right. Yeah. And right, the sensitivity is a function of distance, right? The globular clusters are typically not that nearby, right? So, some of these sources, right, like this white dwarf, for example, right, this is at 200 parsecs, right? The closest globular cluster we're looking at is at 3 kiloparsecs, right? So, other questions? All right, so what can we learn about this candidate M62? This one here. So first of all, there's Hubble data of this globular cluster, because there's Hubble Space Telescope data of almost every globular cluster. And right, you can actually do the astrometry, especially for the radio observations, extremely well. And you find that the X-ray and optical observations precisely match this star here in the center of this very dense globular cluster. And if you look at the location of this star on a color magnitude diagram, right, so this is telling you the stellar temperature, this is telling you the luminosity of the star, you can see it doesn't actually look like it agrees with the color magnitude diagram of the star itself. And that actually could be explained by the presence of an accretion disk with Balmer emission around the star. So we conclude that it looks like the counterpart of this thing is a giant. And that's actually real good that it's a giant, because if you look at this thing here, this is also a giant. So this really looks phenomenologically more and more like this other thing that we know looks like a stellar mass black hole. There's actually maybe a connection between the state of the evolution of the secondary and how bright the quiescent X-ray luminosity is. That has to do with the mass transfer rate. So giants, right, because they're expanding due to their nuclear evolution, that's making them larger with time, more quickly than you expect from a main sequence star. And so that causes the mass transfer rate and thus the quiescent X-ray luminosity to, in general, be a little bit higher for the giants than for secondary counterparts. So this thing is actually pretty bright. If it weren't in the center of a globular cluster, it would be dead easy to get spectroscopy of this thing to figure out what it is. But it is in the center of a globular cluster, so it's hard. So in this case, Anil and I are actually closely collaborating on this object, so we've tried a few different things. And one of the most recent things we've done is actually go straight back to the Hubble Space Telescope. Right? So that's the thing that allowed us to have the photometry to identify the counterpart. Right? We can also do spectroscopy of the Hubble Space Telescope. So I don't know if you know this, right, but Hubble tweets whenever it's observing something. So you can follow Hubble on Twitter, and it will tell you when it's observing your object. So this is back on the 1st of September, just last fall. It told me that it was looking at my star using the Space Telescope imaging spectrograph.
One of our undergrads actually helped write this summer. So
That's so awesome.
Yeah.
This is the best.
Julie Heiding helped write this, the Hubble Live thing.
Yeah. So this is great. So you can see at any time what Hubble is looking at. Yeah, so I retweeted this when it said it was looking at my thing. And we use the spectroscopy to measure the radial velocities of that giant star and that's companion. So what I'm about to show you is extremely preliminary, because there are some various issues with the data. But I can tell you what's happening currently, which is that we measured the radial velocity of the star that's companion. And the best fit we got was something like an orbital period of somewhere between 4 and 5 days, and this large semi-amplitude of several hundred kilometers per second. And you can combine that information, the period and the semi-amplitude, together with g, to get what's called the mass function of the binary, and that essentially sets a lower limit to what the mass of the compact object is. Now, to actually figure out what the mass of the compact object is, right, as Kepler's law would tell you, you also need to know what the mass ratio of the binary is, right, since that compact object has to pull on the secondary, and the inclination of the binary, right? If it's edge on, the signature will be very strong. If it's face on, it could theoretically go to 0 if you were perfectly face on. So that matters. So we ran some simulations of some of these for reasonable parameters to figure out what the best inference for the mass of the compact object was. And so we have a probability density function of the distribution of the mass of the compact object on the preliminary basis on these data. And so I'm just going to you can look at this density function of the mass of the compact object. So there, this red line, this is the most massive neutron star known. That's at 2 solar masses. Right? People say even if you use kind of exotic equations of state for neutron stars, they're not going to get much above 3 solar masses. That's there. The highest black hole mass known in an X-ray binary is about 20 solar masses. Right? That's why the LIGO events are so crazy, and right, the LIGO masses are, sort of out there somewhere. So I would say, right, this is increasing evidence that we really might have a dynamical detection of the small mass black hole in the system. And right, this is actually one of the things Mel and I are working on this week along here. Alright, so that's one candidate. I want to talk about a candidate which is...
Was that linear scale on the y-axis?
Yes, that was a linear scale on the y-axis. Yeah.
It's a really wide range.
That's right. So the inclination for these things is enormously, right, since it goes to sine cubed. Right, there's a very wide range. Yeah, that's right. Right, the goal, of course, is to get an object for which, without any, right, the mass function is 3, and once it's 3, then you know it's a black hole no matter what the inclination and the secondary are. And that's just, has nature been kind to you or not, right? That's the only thing that determines it. So 47 talk, this is the first cluster I showed you that's just chock full of X-ray binaries. And this is, again, a Chandra image. You can see it's just full of binaries. And I know this is what it looked like before, but again, one of these objects in this cluster appears to be a bright radio continuum source. And you can see here, this does not say VLA, this says ATCA. And the reason is that 47 Tech is too far south to be observed from New Mexico. So instead we turn to this radio telescope in Australia. It's called the Australia Telescope Compact Array, which is not as good as the VLA, but it actually also just got upgraded. And so it's actually pretty sensitive. I mean, it's about a factor of 3 worse than the VLA, but it's still pretty good. And since it's a little bit less sensitive, they give you more time to partially compensate for that, so you can get pretty good with that. So where does this source fall in our X-ray and radio correlation? Actually, not all that far from this M6G2 source there. But this one has some peculiar things about it, especially when you look at the X-ray observations of the object. So I didn't show you the X-ray spectrum for the M6G2 source because it was real boring. It just looked like a power law, like flat. That's just what X-ray binary X-ray data look like, and in fact, you can't basically tell neutron stars and black holes apart from X-ray data unless they are showing pulsations or X-ray bursts. If they're just in the normal quiescent state, they look identical. This one looks weird though, so it doesn't just look like you have a power law. There's this weird bump right here, relatively soft energies. And in this paper from about 10 years ago by Craig Heinke, he pointed out that this kind of looked like there was 0.7 or 0.8 emission here, which had never before been seen in a low mass X-ray binary. And he said, well, maybe it's a CV, right? We know that, there might be oxygen around a CV, maybe that makes sense. It doesn't look like any other CV we've ever seen, right? Any other accreting white dwarf, but, maybe that's what it is. It turns out there's also optical spectroscopy that was done in a special slitless mode with the Hubble Space Telescope, but in the far ultraviolet where the density of sources is low enough that you can do these sorts of observations. And you get this spectrum here that has this double-peaked emission, which is this key indication of an accretion disk, right? So if there's an accretion disk that's seen, especially if you see it more edge-on than face-on, you get this double-peaked thing from the two edges of the disk here. And this is a carbon-4 line that you see here. There's no helium emission in this far UV spectrum. And it turns out this is just generally a very UV bright star, where in this UV filter it's super bright, and in the I-band filter, where stars are usually easily seen, it's super faint. So we have this thing, maybe there's evidence for an accretion disk, it's bright in the X-rays, it's kind of bright in the radio. So I told you if there's carbon and oxygen, right, and there's no helium and no evidence for hydrogen, we're back to that sort of super bright thing I showed you at the front, right? It's suggestive that the donor in this particular system is a CO white dwarf. Something giving you carbon and oxygen, but no helium and no hydrogen. And if this were true, it would suggest that this might be what's called an ultra-compact X-ray binary. So there is mass transfer going on, but since the mass is being transferred from a white dwarf, the orbital period of the binary has to be very low, so less than an hour. for it to be an ultra-compact black hole binary. And my postdoc just got X-ray evidence that this might really be what's going on. So you combine several deep X-ray observations and did a periodicity analysis and found that peak in the X-ray spectrum consists of an orbital period of 28.2 minutes, which is exactly what you'd expect if this is an ultra-compact X-ray binary. It's consistent with the X-ray luminosity of the source. And here you can see the kind of ratty X-ray light curve that you get if you focus on this orbital period. So we certainly need more data and more analysis for this source, but it seems plausible that this might be the first ultra-compact black hole X-ray binary that's seen in the Globular cluster. It would be really nice to have more dynamical data on it. Right, the issue is that just from looking at the accretion like this, you can't really distinguish very well between a black hole and a neutron star, right, even though a black hole is more massive. Right, the emission is typically from the edge of the accretion disk. But maybe if we get a nicer spectrum, we could look at the wings. Maybe there might be a higher velocity component that would suggest it was a black hole. So that's something that we're thinking about right now. So I just wanted to point out those two objects in particular to give you a flavor of the sorts of things that we're finding. But right, that's not the limit of what we're finding with our survey. So currently, we have identified 13 of these candidates that show an excess of radio emission compared to their X-ray emission in our Globular cluster sample. Some of them are relatively bright, maybe going up even the 10 to the 34 ergs per second, but some of them are really extremely faint, right? Down here in the 10 to the 30, the 10 to the 32 regime. You'll notice some of them do not lie in this relationship. For example, there are two candidates here in one single Globular cluster, the cluster M22, that we published, that appear to be very radio bright. There's actually now a candidate that was found in the field that's up here too, so maybe that's not too weird, but we're pursuing more observations to understand these things in detail. But I want to emphasize, right, so we have 13 candidates, we've got about 50 clusters, so we have these candidate objects found at about a quarter of our Globular clusters. So these things are not rare. And I know that they're black holes, but they're not rare.
So what's the program that's targeting these clusters in the X-ray? What's the telescope? Who's leading? How's the program organized?
Yeah, so we started with all archival data, right? A lot of these we looked at in detail Chandra, and then our group put together a program to get a bunch of Chandra data for the ones that had not been targeted. So we had a big program, so we now have Chandra data for everything.
But it's single epoch.
It is single epoch, that's right.
You're hoping to catch something in it.
That's right. In some cases where we have a candidate, we've attempted to go back and get simultaneous radio and X-ray data, so we can put it simultaneously on these plots. I gotta tell you, it doesn't really seem like they burble around by a little bit, but we're not seeing like the sort of factor of 10 variations that would cause it to wind up in a very different part of the plot. Whether we've just been lucky or unlucky, or whether that really is genuine behavior, we don't know all that much. So one thing we're doing to address that is we're doing a very detailed study of this thing here, this field V404 thing. So this actually is VLA data that goes back for 25 years. And we're analyzing it to look at the power spectrum, its variability, and then try to see how much our things might be varying if they look like it. Alright, so we found some candidate black holes. That's nice. How does that tie back to the stuff I was talking to at the beginning, right? How can I make total inferences for the black holes population clusters, and that's for the sort of thing they might be doing, right? Like making, LIGO black hole sources. So here, right, we've got to obviously turn to theory. So this is one example of a paper looking at the binary black hole populations of black holes and binaries, comparing them to other black hole populations and clusters. This is Megan Warscher's paper, who works in Fred Razi's group at Northwestern. They've been one of the leading groups doing simulations of black holes inside star clusters the last few years. And the conclusion of this paper, right, where she has a bunch of different models of clusters, each one of them is different, but typically what she found in her paper was that for every black hole that's in a mass transferring binary, she found tons of black holes that had not found themselves in the binaries. And so if we found a black hole in a binary, that probably implied there were, a large number of black holes still in the cluster that didn't happen to be binaries, and though it suggests the Globular clusters would just be chock full of black holes if this were true. The only problem with this is, as much as I would like for this to be true, if you look at what their model Globular clusters look like, the ones like this that have a bunch of black holes in them, they kind of don't look like Milky Way globular clusters. And the issue is that if you've got all those stellar mass black holes packed into the center, they kind of interact with the other stars, they heat up the center, and the globular clusters just end up not looking all that dense. They don't look like things like 47 Tuck. So whether these models and these predictions are really consistent with observations, all the stuff that we know about globular clusters, I think is still very much an ongoing effort. Right, these same groups have been looking at whether these dynamical black hole binaries made inside of globular clusters are actually consistent with the LIGO events. And so this, by Saurabh Chatterjee, was one effort last year to look at how some of the model results for what the chirp masses were for the observed LIGO events, how they compared to some of the different models. And you don't need to know in detail what all these colors are. Mainly, the relevant thing is that they describe metallicity. And so the metallicity strongly controls what the mass of the black holes are. So at high metallicity, you get little black holes. At low metallicity, like in a lot of globular clusters, you get big black holes. And so they're basically predicting something, right? So this is the subthreshold trigger, that you more easily make at low metallicity. Something like this, right? GW 15, 12 to 16, the Boxing Day event. That seems more like a high metallicity thing. And none of their models get to something as massive as the initial one. So, going back to my initial question, right? How do you make a 29 plus 36 solar mass binary black hole merger? Right? At least in these models, it really looks like there is a better case for the other two events. But this is so dependent on the unknown initial masses of the black holes. And that, in turn, is so dependent on our models of how massive stars evolve. And those models are terrible. We just really don't know. So the main thing I would say as a consumer of news about forming black holes or binary black holes is that you should be skeptical. So how do we decide whether dynamical formation is important? So certainly more LIGO detections are going to help. We might need a whole bunch of them. And one thing, something I haven't talked at all about, is the spins. So you are forming these binary black holes in the field. Most of the models, not all, but most of the models, are going to have the black hole spins aligned with the orbital angular momentum, right? Because the two binaries are close, they're interacting with each other. In a globular cluster, it's not that way. So in a globular cluster, when you form them dynamically, there's no, first of all, they might not be spun up at all if they weren't formed in binaries. And second of all, the spins will not be aligned with the orbital axes. So if you ever are actually able to measure the initial, the spins of these binary black holes before they merge, that could give you a clue. But you might need a bunch of events before you can find some good ones. Our point of this is, right, we're going to continue to look for these black holes in Milky Way globular clusters, and obviously try to constrain the masses, right? If we got a mass constraint. If we really pin down one of these as being quite massive, that would be consistent with this idea that more massive things can form in lower metallicity environments, and that helps suggest that dynamical formation of black hole binaries might be important. If you form dynamical black hole binaries, right, there's no mechanism up until they're close to coalescence that will get rid of the initial eccentricity they typically fight for. Once they go through the LIGO band, that's mostly gone, and so it's not detectable. But it's now clear that ELISA, which definitely seems like it's going to be launched, not for 15 years or so, would be able to detect this eccentricity. So I don't know that we want to wait this long, but I think that would be another good clue to what's going on. So just for my spot specifically, I want to leave you knowing that, right, we've detected black hole candidates in about a quarter of our surveyed globular clusters, and for a subset, there is dynamical evidence that they're black holes, maybe even very massive black holes. And so I think dynamical formation of binary black holes really is a plausible origin for many of the LIGO sources that have been found and that are continuing being found. So thank you. Yeah.
You give a lot of luminosities without any error bars or anything like that. I'm a little perplexed at how certain you are about those luminosities.
Yeah, so this is the advantage, right? So this plot here shows...
Why don't you use watts instead of ergs?
Well, I'm an astronomer. Astronomers use ergs. This is the culture I was born into. I was forced to use it. That's what we do for CGS. So this is 10 to the 9, right? A factor of 10 to the 9. This is 9 orders of magnitude in their axis. And on this one, it's 7 orders of magnitude. So when you make plots that have axes that large, the error bars typically, I mean, the error bars are tiny. Not because they're tiny in reality, but just because, right, the axes are giant. You're looking at a huge range in luminosities here.
But there's no interstellar dust or anything like that that perplexes these measurements?
So radio observations are basically impervious to interstellar dust. That's not true for the X-ray luminosities. So those are affected by interstellar dust. You can correct for that by looking at what the optical reddening is. And since we're looking at sources in globular star clusters, we actually have a huge advantage over people that are studying these things in the field, which is that we know how far away they are. So for some of these things that are in the field, the distances actually aren't all that known, and the luminosities are more uncertain. For objects, since they're in globular clusters, we know exactly how far away they are. That helps a lot.
So can you say something else about? So are there going to be? Will there be signatures in LIGO for the spins? I mean, is there any? Are there any models for how you can extract spin from LIGO data?
Yeah, you just need to get the right events. So closer is better, and you need ones that are louder are better. You need things to line up correctly. However, most LIGO people I talk to, they don't think that getting spins is going to be something that comes typically, unless the spins are all super large. If they're more of this mixture of things that are high and low, for example, it's going to be much harder to get them, and they're only going to get good constraints on a relatively small number of objects. So.
But do you know what the signature of the spin will be? I mean, in the LIGO data, when you look at that data, how do you extract spin from?
They do it.
I know it a little bit. Like,
Tell me
so
now.
in the spin, as it's spinning inwards, when you have a strongly spinning black holes, that spin curve becomes you get non-Keplerian effects going on. So that spin curve becomes you get not a sine curve, but you get messier stuff.
Something with some skewness to it.
Yeah. I mean, I've seen like simulations of what it looks like, so in that lead up. So you really want something with a long lead up that will give you.
When you talk about spin, you're really talking about angular momentum,
Right.
not spin, right?
No, so we're talking about two different things, right? One is the black hole spin, right? So the quantity,
Angular momentum, come on.
the quantity in the metric, right? That is spin, and then the other one is the orbital angular momentum of the two black holes, right? For black holes. And, right, whether those are aligned or not, right, is important for figuring out how they form. So. It's actually what surprises me about these things is that when they detect something, it is still so computationally challenging that the parameters they get out of it are different than the ones they get out after they run an analysis over hours or days. And so, like, when the first event happened, they sent out an alert to the LIGO team. They said, this is where you should look. And people went and looked there, and it turned out where they told them to look was totally wrong. Basically, there was almost no overlap between where the banana of the position ended up being and where they told people to look originally, and that was even a pretty bright event. So doing the follow-up is hard.
Given the huge population of potential black holes in a cluster and the tidal forces, why don't you have 6 or 12 or 22? Why always binary?
So right, if you look at the models, they are expecting that a bunch of them are not in binaries at all, and the ones that are in binaries will never see them. Right? So for us to see them, it can't just be in a binary, it has to be a special binary, right? It has to be in a binary that's close enough that it's transferring mass. And so that means it has to be in a binary typically with either a main sequence star or a giant, maybe if it's special, a white dwarf. And actually one way you make it a white dwarf is not from a regular action, but if you have a black hole that hits a giant right in the middle and goes through, you'll expel the envelope entirely and just wind up with a closed white dwarf black hole binary. That might be how things like that are made. So only a subset, even of things that are black hole binaries, will be detectable by us, because we can only see the ones that are actively accreting.
So in the beginning you said that when you look at all these like galactic globular clusters, you see a bunch of like neutron star binaries but no black holes because the black holes are taken out.
Among the bright X-ray sources.
So are the neutron star binaries just like not massive enough to settle into the center and get kicked out?
You're exactly right. So they do mass segregate, but less so than the black holes. And so they are kicked out much less efficiently than the black holes. So some of them probably do kick out, but not as efficiently as for black holes.
So like how do you figure out what the scaling is with mass in terms of like...
So there are, you can run numerical models where you take an initial globular cluster and you can evolve it forward and you can see what it looks like and then you can see how it matches observations. We still don't actually have big enough computers to fully simulate a globular cluster from beginning to end because there are so many stars in them. We're just at the precipice of being able to do that fully. And my guess is we're going to have new conclusions coming out about the dynamical evolution of globular clusters next few years because of that.
Somewhere in the middle, you had a slides talking about the consistency of the data with the metallicity observation.
Metallicity, yeah.
Oh, metallicity.
Yeah. Did I have a metallicity slide? I said
Yeah, I
that.
think you mentioned it.
I think I said it. So
it's not one of them you just hit through.
oh.
I don't know.
Oh, right, I do mention metallicity there.
Right, yeah. So my question is why this is important?
Right. So if you just take a normal star that has the metallicity of the sun, solar metallicity, a very massive star you evolved forward, as the star gets very luminous, the opacity due to the metals in the atmosphere of the star is very high, and it just blows away the entirety of its outer atmosphere. So that when the core collapses to make a black hole at the end of its life, there's just not much left there to turn into a black hole. And so the black holes are relatively low mass. By that same token, as you go to lower metallicities, the opacity for metals are lower, you retain more of the initial star. You do have some winds, but they're less. And so when it becomes a black hole, the black holes end up being more massive. This is entirely a theoretical expectation. It's never been directly observed because we can't measure the masses of individual black holes. Because we just, we can't find individual black holes, right? All we can find are ones in the Milky Way or nearby galaxies. They don't probe a wide range of metallicities. They've all had these weird binary evolution issues where the stars have transferred mass back and forth, and so that's not testable by these standard models. And so if single stars at low metallicity really do make very massive black holes, we expect them to do that in globular clusters, and then maybe they wind up in binaries like the LIGO events.
So when a LIGO event merges, does it stay in the cluster?
So that initial burst of kicking out black holes of globular clusters probably happens no matter what. Some definitely get kicked out. And subset of those will end up being LIGO events. They will end up merging as black hole binaries, I should say that. That doesn't mean they're LIGO events, right? For them to be LIGO events, they have to merge here, nearby, in the local universe. And so to get things that are observable by LIGO, right, either looking at the very edge of the tail of things that were formed and kicked out a very long time ago, or you have to be looking at things that are being formed at the present day. And so which of those wins depends in detail on a bunch of things.
I was more asking about, I know that the binaries receive some kind of kick when they merge together. I don't know what the magnitude of that is. Is it enough to take it out of the globular cluster, or can you get something that two black holes that merge and then two black holes that merge again and build up big black holes?
They can stay in the globular cluster. Yeah. Nobody really agrees on the exact size of what the kick is when the things merge. There probably is one. And the cores of these massive globular clusters, right, the escape velocity is pretty high, but we really don't know.
That's a question. So you mentioned this red dwarf black hole like a binary.
Yeah.
So what would happen to the red dwarf like when the mass becomes lower and lower, it becomes bigger and bigger, and what happens in that?
Yeah, at some point it will, right, so the mass transfer rate will run away. And I think eventually it'll all get, right, so the mass transfer rate will increase, and then it'll go up to Eddington, and then the white dwarf will be gone. For somewhat lower masses, like if you had a neutron star, I think those actually merge, and they can actually make sort of an interesting electromagnetic transient.
But it keeps draining material off because the star expands and gets less mass and everything.
That's right, but they're right. These things that are ultra compact, right? They're emitting gravitational wave radiation and shrinking because of that.
Okay.
Right. Once you need, right, because since the gravitational wave time scale goes as a super high power of the the semi-major axis. If you're really close, only gravitational waves matter, and if you're really far away, it doesn't matter at all. Right? There's very little regime where it's only partially important.
Did you
saying that mass goes back and forth? Or was that just
When I talked about the evolution of massive binaries, mass goes back and forth. That's right. So right, one of the stars evolves at the very start. It gets big, it dumps mass onto its companion. Then it will go supernova, and then when this star gets massive, it will dump mass back the other direction. So they do donate mass both directions.
until one becomes a black hole?
Depending on exactly what happens, it can actually happen multiple times because the evolution of these stars is very complicated. So it's
Once one becomes a black hole, you're not getting mass back up.
That's right. Mass does not come from a black hole on the other star. That would be a remarkable observation.
That's pretty complicated.
All right, let's thank Jay again. Jay will be around tomorrow, so if you want to talk to him, let me know. We're taking him out to dinner. Also, we have a heat seminar tomorrow on the Large Synoptic Survey Telescope at 11 in the INCC auditorium.
Yeah. Yeah, that's right. It goes back and forth as the stars. So, you know, like the sun.